From the Oregon State University Extension Service, this is Pollination, a podcast that tells the stories of researchers, land managers, and concerned citizens making bold strides to improve the health of pollinators. I'm your host, Dr. Adoni Melathopoulos, Assistant Professor in Pollinator Health in the Department of Horticulture. Spring is on the horizon, folks. I can see it. It's just over there. And that's a sign that I need to get an order in to my bee supply company so that I have some extra queens. Honeybee queens are a engine of a bee colony. If you have extra queens, you can divide colonies in half. They're super useful. Everybody wants them. And, when I get my queens, I'm always excited to get them. But my next guest said there's something about those queens that you might not notice on first glance about their quality. Dr. Allison McAfee is a postdoctoral research scholar at North Carolina State University. She's no stranger to Oregon. She's come and spoken to us in Hood River at the State Bee Association in the past. She has done some really great research. She's working in a collaborative team in Canada and the United States, looking at queen quality, specifically temperature. Apparently, honeybee queens don't experience a constant temperature when they're being shipped, and that can be really disastrous to the quality of that queen, her acceptance, and her ability to do her job. So without further ado, this week on Pollination, I'm excited to invite Dr. Allison McAfee. Okay, well, welcome to Pollination. I'm so glad to finally have you on the show.
Yeah, thanks very much for having me.
Now, if you pick up any beekeeping magazine, it's there in the last few pages. You read about the genetics of the queen. There's all these kind of like super queens out there. But there seems to be a lot less fanfare about other qualities of the queens in those advertisements. So to begin with, can you explain some of the other non-genetic factors that make up a high quality, high performing queen?
Yeah, for sure. I would say ultimately her fertility is the most important factor. She could have all the VSH genetics in the world, but if she hasn't acquired enough sperm during mating, and if those sperm have died off, then she can't lay enough eggs to support a strong colony, and the VSH genetics won't do you any good then. So she'll have a shorter lifespan if she doesn't have as many sperm. And we don't usually think about this, but queens are also susceptible to pathogens like viruses or nosema. And we don't know a whole lot about exactly what these pathogens are doing to affect queen quality, but I have a pretty strong suspicion that they're important.
Well, I can just imagine that, like you say, VSH, these Varroa sensitive hygiene bred queens with these genetics that can, deal with Varroa mites. But if they don't have enough sperm in them, then, clearly they're not going to last very long. But I thought the other thing you said that was really notable is a queen's a really long lived insect. And if she has a virus or something at the beginning of her life, that might over time show up in terms of like the colony's ability to grow and all of those things. So those are, I guess, invisible to you when you pick up a queen and you look her in the snout. You have no sense of those things.
Yeah, that's right. That's actually a new direction that we will be taking our research, is to look more into pathogens, because part of this queen survey that I've been doing over the last couple years in BC has shown us that failed queens usually have higher levels of viruses. So we don't know if there's a cause and effect relationship there, but it's, I think, a good enough reason to me anyway to look into it more.
Okay. Well, that's great. Well, I guess the first, I want to pick up on that first thing that you mentioned is that, quality may have to do with her fertility and whether her spermatheca is full of high quality sperm. For those of our listeners who are unfamiliar with this fancy word spermatheca, can you explain what it is and why it's important?
Yeah, absolutely. So if you don't know what a spermatheca is, don't worry. I did a whole PhD on bees, and I knew what a spermatheca was, but I didn't know much more than the fact that that's where queens store their sperm. So it's a highly specialized sperm storage organ, and actually most insects and even some amphibians have spermathecae. But in queen honeybees, it's particularly well developed. So what it actually looks like is just like a little pearl in her abdomen, inside her abdomen. And it's about the size, maybe half the size of a pinhead.
Wow.
Just over a millimeter wide, if you can imagine that.
Okay.
And when the queen mates, the sperm she acquires from the drones will migrate into that spermatheca and fills it up about halfway, and the rest of the spermatheca is filled with this stuff called the spermathecal fluid. And that's kind of like a bath that creates the best environment to keep the sperm alive for a very, very long time.
What do you mean very, very long time?
Well, the lifespan of the queen. So in the order of years, people throw around the number of queens live up to 5 years a lot, but I think most beekeepers these days would say, well, typically actually more like 2 if you're lucky.
That's remarkable. Imagine anybody who's, goes to fertility clinic, like that stuff's fragile. Like you have to freeze it or handle it, but it's in a living organ for years and it's still good. That's pretty cool. That's amazing.
Yeah, that is the main reason why I wanted to start doing research on queens, actually, is just because it is such an extreme feat of biology to be able to keep sperm alive for that long. It's really only rivaled by ants, which take it to the next level. They can store sperm for decades. But
is that right? Wow. Okay. So we're on the high level there in terms of sperm living sperm preservation, and I can imagine one of the reasons that a queen doesn't have enough in there is she's just poorly mated, which is is one issue. But I imagine I was going to point out that you're a lead author on a paper that came out last year that is even if that spermatheca was full of really good quality sperm, it may not survive if the queen is exposed to heat stress. So how on earth does a queen get overheated? Isn't the colony temperature tightly maintained? Like, how is that even possible? How does a queen get overheated to the point her sperm may be impacted?
Yeah, that's a really good question. And you point out that usually we think about colonies as being these really highly thermoregulated environments, and the workers do an excellent job of keeping the temperature pretty steady, somewhere around 33 to 36 degrees. But there are 2 ways that queens could become temperature stressed. And the first one is because we like to take queens out of their colonies, put them in little cages, and then ship them all over the world. And when they're in those little cages, there are only a few attendants, and they're almost totally vulnerable to just whatever the temperature is outside, whether they're in the cargo hold of a plane or in the back of a UPS van or on the dash of your truck. They can't really thermoregulate because there are just so few bees in there. So that's one time when they may be quite vulnerable to both cold and hot, both extremes. And we've tracked the temperatures in shipments quite a few times now, and we see somewhere, it depends exactly like what kind of shipments we're looking at, but we usually see a temperature spike happen in 1 out of every 10 or so shipments that we send.
Is it that frequent? That's really amazing and shocking, actually.
Yeah. I think that we've just been pretty unaware of this as being a substantial risk for a long time. It shouldn't be all that surprising that heat stress kills sperm for honeybees, because that is true for so many other animals as well, including people. But I think we just kind of didn't really think about what can happen during shipping.
Absolutely. You did mention, though, that you said there was two circumstances. What's the second one?
Yeah. So the second one is that, I'm starting to think that honeybee colonies are maybe not as good at thermoregulating as we think they are. And we have some data from colonies in California during a heat wave that showed that the temperature inside the colony, and this was a standard 10 frame deep, like wooden box colony, the temperature 3 frames in from the outside was still getting to be above 38 degrees Celsius.
Oh, really?
And like I said, it was a heat wave, so it was really, really hot outside. It was like 45 degrees outside. But the reason why this worries me is because with climate change happening, we should only expect more and more heat waves, and for them to be more intense as well. So that'll cause an added problem for the colonies as time goes on. But also, we're not always dealing with 10 frame deep colonies. We're also keeping bees in 5 frame nukes, in little mating nukes. So those we would expect to be even more challenged by extreme temperatures. And if you think about a 5 frame mating nuke, you can only get 3 frames in from the outside, right? You can't get any deeper in the brood nest than that. And in the bigger colonies, that was kind of the thermoregulating limit, was that like really central core. So you just don't have that. You don't have enough space. You don't have enough bees in a 5 frame mating nuke even, and they get even smaller.
Yeah, I can just imagine there's just no capacity to buffer, because it's just the edge is so close, and hot temperature outside would, come. The queen's going to invariably going to be exposed.
Yeah, there's nowhere to go in that smaller space.
So it does raise the question. So does temperature matter? Tell us what you found.
Yeah, temperature definitely matters. So probably the most useful information is that we got from our data is that the temperature range between 15 and 38 degrees Celsius is like the safe range. And that's actually quite a big range, but it's still we still need to be careful about how we keep our queens and what they might be exposed to in really extreme weather events.
What would just repeat those temperatures again? So you said.
Yeah, it's between 15 degrees and 38 degrees.
Okay.
So anything, you can imagine the sort of tolerance range in terms of keeping sperm alive as being like a bell curve, like an inverted, just like a bowl where there's a maximum somewhere in the middle. And that maximum is around the temperature of the brood nest. And then as you get farther and farther away from that, then the risk of damaging the sperm gets greater and greater. And so
I'll just stop you for a second, as I'm a Canadian as well, and I know everybody's like, what did you say? So we're talking about like 60 Fahrenheit to what was the centigrade again? What was that safe zone? That higher end was
38 degrees.
38. So we're talking. Okay, thanks. That's 60 Fahrenheit to 100 Fahrenheit. I still can't do it in my head, Allison. I'm pretty useless at this imperial metric.
Honestly, I don't even try. Okay, because I don't want to get it wrong.
But like you said, it's a bell curve. It's kind of like the optimal is in the middle, and then on those, the extreme goes. Those temperatures from 100 to 60 are the extremes, and then when you get beyond that, that's where things seem to happen.
Yeah, that's right. And I should say also that the way that we came up with this range as being the cutoff is, so just imagine again that bell curve, and you start at some really high level of sperm viability. And as you get farther away from that optimal temperature, the viability will drop and drop and drop. And then you have a question of, okay, how much of a drop is too much? Like how much can happen before I really need to worry? And so we set that threshold to be 11%. That's like an 11% drop in sperm viability, because that was the difference that we found when we compared sperm viability of failed queens and healthy queens. So that is an amount that we think is probably biologically relevant.
Let me get this straight. So as soon as you drop below 11% viability, then you start to have queens go missing, and there's all sorts of problems when you go below, above that threshold. So that's why you set the bell curve the way that you did.
Yeah, exactly.
Okay. So, and the one thing I did want to ask, it goes in both directions. So too cool is a problem too.
That's right. Yeah. And our data actually suggests that cold temperature spikes are probably more frequent when the queens are shipped. We don't often see the increases in temperature, which I guess makes sense. When queens are shipped commercially, they're spending most of their time in a plane or in a warehouse, and those tend to be very cold environments.
With that bell curve in mind, I think earlier in the episode you said, these extreme temperatures happen 1 in 10 shipments. This is what we're talking about. There's 1 in 10 shipments are going to be either below or above that bell curve.
Yeah, that's right. And for a couple hours or more, that's sort of the duration threshold that it takes to really cause damage to the sperm.
Okay. All right. Perfect. Well, I guess, raises this question. I buy a queen, and I have no idea when I see the queen and I pick it up from the supply place or, get it in the mail. I can't tell what temperature she was exposed to. And it sounds like from the paper, you have extensive experience with molecular biology techniques. You're a wizard when it comes to these techniques. And you've been able to develop some tools using these techniques to screen. Can you tell us a little bit about what you did to kind of develop these tools and how you envision they may turn into something that beekeepers can use?
Yeah, absolutely. So my long-term vision is to be able to take a queen from a beekeeper, a failed queen, and run a series of molecular tests on her tissues, and then look for different markers for different kinds of stress. So the idea is that I'd be able to look at this data and then tell the beekeeper what the most likely cause of her failure was. So kind of like a molecular autopsy. And to start to do that, I took queens into the laboratory and I stressed them in a very controlled way. So I had a group of queens that were cold shocked. So I essentially put them in the fridge, which is 4 degrees Celsius, for 2 hours. I had queens that I heat shocked at 42 degrees Celsius for 2 hours. And I had queens that I applied a pesticide stress to. And that pesticide stress was actually, it wasn't just one pesticide. It was a mixture or cocktail of the kinds of things that we tend to see in wax. And then I compared the proteins that become activated in those stressed queens to control queens that were just not stressed at all. And so what I was looking for was some kind of protein indicator that would show up in the stressed queens that wasn't in the control queens. And it was very important that those proteins would be different for different stressors so that I could distinguish between them. So I came up with a panel of 6 different proteins, so 2 for each stressor that are all unique. And the idea is that now I can start looking for those in failed queens to get an idea of what's been happening to them. But this is maybe a cautionary tale, because once I found these proteins, I thought, great, I have a diagnostic panel. I can start to get an idea of what's happening to our queens. And then I looked for them in failed queens just to see how they compared to this group of healthy queens that I had, and was surprised to see so many of them with the indicators of heat stress. And that really didn't make too much sense to me because I didn't expect these queens to be exposed that frequently here in BC. Mm-hmm. It was much more than 1 in 10. It was like 50% of the failed queens had these heat stress markers. So then I started wondering if they could be related to some other stressor that I just hadn't measured yet or hadn't thought of.
Yeah.
And a student in the lab actually did viral analysis on these queens. And what I found was that the exact same proteins that are linked to heat stress also actually are apparently an antiviral response. So now I need to go back to the drawing board and come up with new heat stress markers. But this is very much a work in progress. And it's super interesting, actually, anyway, that these same proteins that can help mitigate heat stress are also linked to immunity against pathogens. I think there's some really interesting biology there.
I am admittedly so out of touch with proteomic technology. I don't know what a stress protein is. What if you were to describe to the listener? I know when I'm stressed, I take a squeezy ball. There is an index of my stress. But what is a stress protein? What are these proteins like? What do they regularly do in the organism?
Sure. So inside our cells, proteins are really the molecules that do most of the important jobs. So they'll do things like replicate our DNA when cells are dividing. Antibodies are proteins that help us fight off disease.
Oh, yeah.
They're kind of like the little molecular machines in our cells. And when we, say, eat food or get sick or have some kind of biological stimulus like that, our bodies can respond by producing more or less of certain proteins.
Oh.
So when you get sick with a pathogen, you will respond by producing more antibodies, which helps you fight off that disease, for example.
And so if they wanted to see like, is this person infected, they could measure the production of these antibodies. Well, that's clear. That's what people do. You look at these antibodies and you can say, this person has an infection or something. So it's a similar.
Exactly.
Oh, okay.
Exactly. So a queen that has been heat stressed or exposed to pesticides will produce a set of proteins that just helps them deal with that stress. So, for example, with the pesticides, they will often upregulate detoxification enzymes, so enzymes that will help clear out that pesticide. With heat stress, what that does at like a cellular level is it increases risk of this thing called oxidative stress, and that can be really bad for cells because it damages the DNA. And a very kind of normal response is for the cells to produce these heat shock proteins, which will kind of like help mop up these reactive oxygen species that cause that damage. So those are just some examples of what a stress protein could be. It's just any protein that is produced in response to a stressful stimulus.
And I guess that's great. That's very helpful. And that's why you had the hypothesis originally. There should be a protein that's very specific to this syndrome of queens getting overheated or cooled down. And so, but what you found was, unfortunately, the things that you couldn't find something specific. And I guess that's why the pesticide was in there as a kind of like, it should be different from the ones that whatever I detect should be different from the ones that, pop up in the presence of a pesticide exposure.
Yeah, exactly. And I don't want my stress proteins to just be produced no matter what the stress is. I want something that is produced specifically in response to like one kind of stress or another, because my whole goal is to be able to like do molecular detective work and try to figure out what happened to the queens. And it's just not very useful if all I know is that she was stressed somehow, but I have no idea how.
Okay, great. So if this is the vision, is that you would have kind of a kind of fingerprint for each one of these maladies, and a beekeeper can send a queen in and say, what happened to her? And you could say, well, I can tell you it was X, Y, and Z, or, that's very cool.
Exactly. Yeah.
Let's take a quick break. We've got a set of questions we ask all our guests. I'm very excited to hear what your answers are. We'll be back in just a minute. Okay, we're back. I always love the breaks. It gives us a chance to talk. And I realize I'd sent you some questions in advance, and I didn't quite follow the question. And I guess one of the questions I set up is like, in a queen's development, there's not a lot that can go wrong. But you went back to Mark Winston's Biology of the Honeybee, and you wanted to bring something up I thought was cool.
Yeah, so I think it's maybe a bit of a misconception that the amount of sperm that a queen can acquire is really only influenced by her mating success. There's actually something else that can directly influence how much sperm she can acquire. And if you rear your own queens, then you might remember that when you were learning grafting techniques that we're supposed to graft really, really young larvae. Like somebody, when I was learning, they told me the best larva to graft is one that you can't see because they're so tiny when they're at that newly hatched
stage. Can I
stage.
just stop you for a second? Who taught you how to graft?
Oh my goodness.
Was it Heather?
Now this is going back in the memory banks. His name was John, but his last name was,
Jabot?
That would be really useful here. In Salmon Arm, he ran a queen rearing course in Salmon Arm.
Oh, I know the guy.
First year of grad school.
Oh yeah, I remember him. Anyways, it'll come to me as we're going. The reason I asked is because we did have Heather Higo on an earlier. Heather was the one who taught me how to graft. I know you've worked with Heather in the past, but anyways, so we know John, whatever his name is, up in Salmon Arm. I know what you're talking about, but so he told you, you can barely see them, and so if you graft any later, okay, pick up the story.
Yeah, so the reason why we should graft young larvae is because the earlier that they are given that queen diet, so they're just fed explicitly the royal jelly, the earlier they start on that diet, the bigger the spermatheca they will later have as adults, along with many other physiological differences. But you can imagine the bigger a spermatheca you have, the more sperm you can fit in there, theoretically. So that's maybe one of the first determinants of the amount and quality of the sperm that a queen can acquire. It starts way back when they're only 1 day old.
Yeah, that's awesome. The other thing that we were talking about at the break was I wondered aloud then. I was like, well, if you take it all the way to the extreme, does a worker have like a vestigial spermatheca? And I think you said that you believe that there was.
Yeah, they do. They're very, very tiny. I've never seen one with my naked eyes, but I have read about them. I've read that they exist.
Fascinating. It wasn't John Gates, was it?
Yeah, it was.
All right. Well, listeners, there is an episode with John Gates, the king of Southern British Columbia queen rearing. So check it out. Awesome.
I'm so glad you remembered.
This is bugging me. Okay, so I got 3 questions for you. The first one is, and I imagine you've got all sorts of ideas, but do you have a book recommendation? We just talked about a great book, Biology of the Honeybee, but do you have a book recommendation for our listeners?
Yeah, so I don't often read honeybee books, just like I don't often listen to honeybee podcasts. I think because when you spend the majority of your day already thinking so much about honeybees, at the end of the day, you kind of just want to focus on something else.
It took me until I really started working with native bees to pick up a jar of honey again. I'm totally with you.
Yeah. Okay. I'm similar to that. So my book recommendation is not actually explicitly a honeybee book, but it's a book that I'm rereading right now. It's called Prodigal Summer by Barbara Kingsolver.
Oh.
And it's one of my favorite books. It's a really interesting story of many different people, all from kind of all different walks of life. There's a farmer, there's a geneticist, there's a parks employee, who are all living in this really small valley that's very close to nature, somewhere in the southern Appalachian Mountains area. And so it's very ecology focused. So I think it's still appropriate to bring up here, but it's just a neat weaving of the different ways that these different people all interact with the same nature that is around them.
And they're, very different people.
Yeah, exactly. Yeah. All with very different opinions.
Wow. That's great. Thank you so much. That's a great recommendation. And I was trying to think, I remember visiting Tammy Horn in Kentucky, and I think I remember Barbara Kingsolver being from Kentucky or something like that.
I don't know.
I've read one of her books, but the one about Trotsky, which was good.
Yes, she grew up in Kentucky. You're correct.
All right. Whoa. Well, okay. So that's a great recommendation. Hasn't been recommended before. Check it out. Our next, the next question we have for you is: do you have a go-to tool? Like, if you really had to choose, what would be your go-to tool?
Yeah, it actually wasn't hard for me to come up with this one because I don't really have much that's outside of just the standard beekeeping gear. But my favorite tool, I think, is my little pocket torch, which is like a blowtorch, but it's small enough that it can fit in your pocket. So it's super useful because it's just so small, but yet still just really easy to light your smoker with it, or sterilize your hive tool, which, you can't really do with just a lighter. And sometimes a blowtorch is just annoying to carry around with you.
So is it like butane filled? Is that how you?
Yeah.
Be darned. I remember when I was in the Winston lab so many years ago, it was like a book of matches. Like, Mark was cheap back then, and sort of like, and I was like, lighting a smoker with a book of matches is like, maybe Mark, in his wisdom was trying to teach us a life lesson, which wouldn't be beyond his character. But I was thinking, like, but as soon as I was introduced to a torch, you could really get a smoker going well under all conditions. It really makes life so much simpler.
Yeah, agreed. Yeah. I would curse myself when I would forget to bring it with me and I had to light the smoker with just a lighter, let alone a book of matches.
How small is this thing? You can fit it in your bee suit pocket?
Yeah. It goes in that pocket, no problem. It was actually,
that's great.
It was Steve and Mike from Delta Honey Farms who gave this to me as a gift. So shout out to them for introducing me.
I always love that, hanging out with beekeepers, because they've got, you use that for that. That's so clever. Yeah. Okay, well, that's great. I always remember, Liz Huckster was the one who taught me to, keep those mini marshmallows in your truck for emergency queen plugging, cage plugging.
Oh my goodness, that's such a good idea, and I hadn't heard that before.
They never go bad. You can have them there for 20 years. Don't eat them after 20 years. Okay, the last question I have for you is, do you have a favorite pollinator species? And I always squeamish asking this question around people who work with honeybees, but I'm always surprised that people have all sorts of interests outside of honeybees.
Yeah, well, you don't need to be squeamish asking me that. This was also very easy for me to answer. It's definitely any species of bumblebee is my favorite. And the reason why is because I also really, really like to hike. So I spend like almost all my free time that I have when the weather's nice outside trying to get up a mountain. And I love the alpine bumblebees. I don't even know what species there are up there, but I know there are many because you just see such big diversity between the different sizes and colors of them. But they're my favorite because up there in the mountains, it can be really cold sometimes. And the bumblebees are they're so like determined that they are caught outside in the cold on these flowers, and they're so slow that you can just like interact with them in a really more intimate way than you could ever interact with a honeybee.
Isn't that right? Yeah.
Slow alpine bumblebees specifically are my favorite pollinators.
That's a great choice. And my bedtime reading these days is I'm rereading Bumblebee Economics, and I realize that these, unlike honeybees, these are bees that experience wide temperature fluctuations. I do wonder about this, how they deal with this problem of temperature extremes in their sperm when the queens have mated and they kind of go underground for the winter. I wonder how that all works out.
Yeah, to bring it full circle, right? Different bumblebee species are better or worse at dealing with heat stress too. It makes sense that they're more hardy to cold given their life cycle. But some of them, I think it's B. terrestris. I'm not 100% sure, but there's one fairly common species of bumblebee that just seems to be resistant to heat stress.
Oh, isn't that cool?
Yeah.
This has been a real delightful half hour talking with you. Good luck on pursuing down those leads. It's always a pleasure. Take care.
Thank you. Thanks for having me.
Thank you so much for listening. The show is produced by Quinn Sinan Neal, who's a student here at OSU in the New Media Communications program, and the show wouldn't even be possible without the support of the Oregon Legislature, the Foundation for Food and Agricultural Research, and Western SARE. Show notes with links mentioned on each episode are available on the website, which is at pollination.podcast.oregonstate.edu. I also love hearing from you, and there's several ways to connect with me. The first one is you can visit the website and leave an episode-specific comment. You can suggest a future guest or topic, or ask a question that could be featured in a future episode. But you can do the same things on Twitter, Instagram, or Facebook by visiting the Oregon Bee Project. Thanks so much for listening, and see you next week.